Over the past couple of weeks in quarantine, I've been working on that. A completely custom, 3D printed, 7-segment display clock. Why, you might ask? Well, because I wanted to learn as many new things as thoroughly as possible over this crazy summer. In this video, I'm going to show you my original idea, how I worked towards it, and all of the many, many challenges that I faced along the way. Let's get started. This is the end result. I'm quite happy with how it turned out, but getting to this point took quite a few iterations. If I had to pick one thing to critique about it, I'd say that I would have liked it to be a little bigger, but the price of PCBs tends to increase exponentially with the size, and it seems to fit quite nice over my closet door frame. I think that in the end I struck a pretty good balance between cost and features. Not accounting for the bulk ordering of PCBs, I think that the electronics inside are worth about $50 plus filament, which for a one-off project isn't that bad. But now that you know how it turns out, let's rewind a little bit to a couple of weeks ago. Now that I have more time on my hands than I know what to do with, instead of just playing Beat Saber or CSGO for another 100 hours, I decided to make myself just a little bit useful and put my knowledge of programming and design to the test. I've been interested in making a larger scale LED project for a long time, and after years of tinkering with a Raspberry Pi, this idea was one that consistently stuck out in my head while still seeming doable in a relatively short time frame. As for features, I pretty much knew what I wanted from the start. External design-wise, it had to be able to set its own time, most likely through an internet connection. It had to be fast enough to update the display multiple times per second, and it had to be powered through USB at a pretty low wattage. As for the modes, I tried to think about what would give me the most information with the least amount of outside contact. In the end, I settled on having 5 modes. 1 for local time, 1 for UTC time, 2 that display temperatures, both in Fahrenheit and Celsius, indoor and outdoor, and 1 that displays the humidity as a percentage. Why might I want both Fahrenheit and Celsius, you might ask? Well, I don't know, I just thought it would look cool, and here we are now. Worst case in the future, if I don't like it, I can just comment out a couple of lines of code and voila. Other than that, it's pretty basic, just showing the hours, minutes, and seconds with a reasonable amount of accuracy. This certainly isn't a Matillion clock. Now that you've seen a glimpse of the final product and my goals in production, let's go in depth with my design and manufacturing process. I originally started working on this project all the way back in late 2019, but I wasn't able to finish it at the time because of my schoolwork. Once school ended, however, I became increasingly invested in this project and my ambitions slowly grew. At first, I saw myself using pre-made 7-segment displays like you'd find in microwaves or other small electronics and make it into a tiny little always-on desk piece. But after I realized how many small wires I would need to hand solder together and the complexity of designing something that small, I decided to completely change directions and experiment with creating a much larger display that uses 5mm LEDs and a 3D printed diffusion layer instead. It was also at this point that I realized I had a problem. I knew basically nothing about designing for tons of LEDs or a low power device. My initial reaction was to limit the clock to 4 or even 2 digits so that I could connect each LED directly to a Raspberry Pi. Although I was able to get a prototype working, in the long run this wouldn't work and most definitely would not have been worth the enormous effort of referencing pins and all the manual calculations and programming that I would have needed to do. Plus, the Raspberry Pi would have maxed out almost any USB power supply I used on its own, without even accounting for the LEDs. The problem was that although I knew an Arduino would probably be a better option on all fronts, I had absolutely no experience with them and had nothing to test or design with. I'd only ever used a Raspberry Pi, and to this day I still don't even have a normal Arduino Uno. Enter the ESP12, the middle child between the ubiquitous ESP8266 and the extravagant ESP32. It integrates simple Wi-Fi connectivity, programming through the Arduino IDE, and enough pins to comfortably run everything I want. For me, this served as the perfect point to jump off from into the Arduino world, while still giving me all the features that I needed. Once I knew what the general design was, I now needed to work on making it reasonably manufacturable. This meant that it was time to create and test the design in CAD and then learn how to create my own PCBs from scratch. This took quite a while, and after testing the design with varying thicknesses of plastics over and over, I came up with this, which I'm pretty happy with. The LEDs are visible in most conditions and give off a pretty uniform brightness when on, and the front looks completely flat when the LEDs are off. As for the PCBs, I already had a little bit of experience in electrical design from circuits and physics and some previous work in AutoCAD, but this was still a whole new level for me. I probably spent an entire week's worth of work just learning the different tools and commands in Eagle and how to link nets together, and just double and triple checking all of my pinouts and board layouts. And during that process, it came time to test my design on a breadboard. After all, I'm not going to put faith in my newly learned abilities and buy $50 worth of PCBs from China without at least seeing if things have a chance of working first. Breadboards are so nice because they allow you to just take some wires and string together a design in a couple of minutes with stuff you have laying around, while still being true to your final product. And I'm glad I did test things here, because not only did testing my design give me confidence in programming with Arduino, but it also highlighted some flaws that would have been a pain to troubleshoot and fix on a PCB, but were easy to fix here just by swapping a couple wires around. Things like missing resistors that led to inconsistent sensor readings and resets, pins that were connected to incompatible interfaces, and most importantly, a way to properly program the ESP12 in the first place. Once all of those issues were fixed, though, and I had quadruple checked the files, it had come time to order the PCBs and begin the final assembly. So here we are. And so, the time has come. Assuming everything goes smoothly, which I hope it does, we should be able to solder everything together and run a quick test using my existing breadboard parts and turn these into that. Here we go. Ta-da! Wow, that is dense. Let's hope they work. Sorry, the neighbor's mowing at the moment, so it might be a little bit loud, but oh well. So I'm kind of proud of this. This is the secondary, this is what actually does the voltage regulation. It's just a little buck boost board with a potentiometer that I'm going to set. But in order to attach it on there, and you'll notice it's on there pretty good, I defined it as a surface mount. So all I have to do is, solder through the existing holes and it'll connect through. If I test for continuity, right, seems to connect pretty well. After much love, I was able to get the controller PCB working, but I did have to connect it to the breadboard for some debugging. Notice that the old one is gone, but it's working now, so I'm going to continue on to the LED boards. It took a lot longer than I hoped it would, but in the end, I got everything I needed to soldered. I did have a couple mishaps along the way. I figured out that if you put too much heat On the shift registers, while they're being soldered into place, they tend to just go out, and I had 3 or 4 of them go out like that. Luckily, only 2 boards, and I had 4 extras. Only thing is I lost a couple LEDs, which stinks. I also had one more error in the PCB design themselves. I didn't connect the LEDs to ground, but I connected them to each other, so lucky for me that only takes one small little bodge wire to fix. Other than that, seems to work great. I want to put them all together real quick, hold on. And here we are. Altogether, it's a little bit longer than I was expecting, and you can see there's a little bit of variation and play, but that should be taken care of when I mount it all together with the 3D printed parts. Here's the back. I'm going to plug it all in now. Look at that. And here's the front. There it is. All of them are lit up. The status LEDs are working, but I haven't finished programming, so it all is pretty much gibberish right now. Cool. Now comes the long part. Wow, this took a lot longer than I was expecting, but after a week's worth of printing, I can finally say that I'm almost done. All things considered, the actual assembly went pretty smoothly. I don't have any footage to show here because I put it all together as I got it done and got it printed, but I think the result should speak for itself here. Looks pretty nice. The reason why it took so long is that I had to reprint several of the pieces multiple times to get the fit right. Specifically these ticker joining pieces, I, for whatever reason, had got the numbers wrong, and I have to space this out just a little bit more. No big deal. I also ran into a weird issue where on the first layer, for whatever reason, my 3D printer decided to just put out a little bit of burned plastic, which was annoying, and it left a blemish here, but in the future I can reprint this, no problem. But other than that, everything is together, and it's looking pretty good in my opinion. You may have noticed that it's not displaying the time, but is actually just counting to 99 over and over, and that's because I have just been running my test program the whole time. I don't actually have the real program done, so I should probably get on that. I'm not going to bore you with the gritty details, but I am going to give you an overview at the end of what every little bit does, so let's get started. Here we are in the Arduino IDE. This is still pretty new to me, so feel free to correct me in the comments if you notice something that I could be doing better. I will also post a link to a GitHub repository with all of my files and dependencies if you want to improve my design or even make one for yourself. But now that it's working roughly how I'd envisioned, I'll briefly cover how it works. Because I'm using shift registers, in order to actually display numbers, I have to define what LEDs should be assigned. In order to do that, I have to convert the binary values that line up with each LED into hexadecimal, and then push them onto the shift register using the Arduino shift out command. By doing this, as long as I send 7 sets of 8 at a time, everything should work correctly and nothing should be garbled, at least in theory. In order to get the time, the ESP12 connects to the internet and just pings an NTP server. No real-time clock needed. That's pretty easy to implement and only really takes a couple of lines of code. From there, all we need to do is just ask the library for the current UTC time and maybe convert it into local time, and that's it. For the outside temperature and humidity, the ESP12 contacts the Open Weather Map API, which seems to keep pretty accurate, more or less. For the inside temperature, the ESP12 just has to read from its local DHT11 sensor. That's about it. Other than that, the program only has to worry about keeping an active connection, handling the brightness based on the light sensor, handling API calls, and making sure that the time and temperature are as accurate as possible. I've abstracted most of it, so any changes I might want to make down the line should be pretty easy to implement. And so here it is. I'll let it cycle through each of its different modes now, starting with the CST time, then moving to UTC time, the measured temperature in Fahrenheit, the measured temperature in Celsius, and the humidity. For those last three, the left value is outside from the Open Weather Map API, and the right one is local from the sensor. I'll also show the automatic brightness adjustment here by turning off the lights real quick. But there it is. Not too bad if I do say so myself. I just hope it lasts. On that topic, looking back from a design perspective, there are definitely some things that I could have done better. A proper 3.3 volt regulator instead of a buck boost board would have been better, and the shift registers that I'm using aren't really designed to push the current of 8 LEDs each, especially without a current limiting resistor. But the modular component of the design should make it easy enough to replace should something go wrong. You also may have noticed that there's a bit of garbage data between fades. I'm still trying to fix it, but I think it's a symptom of the PWM interrupting the clock and data lines of the actual shift registers, but those are all things to fix in a version 2, and there are ways around them. Overall though, I'm quite happy with the result, and I think it's something that I can be proud of. Once again, I've put all of my design files in a GitHub repository in the description, and if you found this video at all interesting or entertaining, I would implore you to leave a like and or subscribe. I have some more LED and electronics related projects that I want to work on next, including some DIY LED nanoleaf panels that I'm going to make from scratch using the knowledge that I learned here. In fact, I'm going to make those to enhance my streaming setup, which I stream at twitch.tv/ZinSweeney, so if you're interested in that too, come by and say hi. Anyways, that's all I have for today, so I'll see y'all next time. Goodbye.